Hello, everyone, and welcome back to the science class. Today, we're going to be talking all about Q equals mc delta T. Now, if you learned anything about thermochemistry so far, you know that this equation right over here is one of the key components of passing the thermochem unit in any high school chemistry class. So before we get started on using Q equals mc delta T, if you're one of my students, you know that one of my pet peeves is mistaking temperature for heat. So if you look, temperature does not equal heat. Temperature, rather, is a measure of average kinetic energy within a system. Heat is just the transfer of energy. So, first things first, in order to really understand thermochemistry, we have to notice the difference between these two, because often there's a misconception that temperature and heat are interchangeable. Now, when heat increases in the system, generally speaking, temperature will also increase, but that's not always the case. And we'll talk about that when we go over heating and cooling curves. Before we get started into solving some Q equals mc delta T problems, let's first define these variables. So what is Q? Q is heat. And the units for these are in joules, or they can be in kilojoules. M should be pretty obvious. M is mass. Typically, we use grams. What about C? C is something that we don't see that often, except in thermochemistry. So C is the specific heat, which I'm just going to put SH here. And the units for these are joules per gram per degree Celsius. Delta T. Now, we should know that T is equal to temperature. However, what does this delta actually mean? So delta, anytime you see this in chemistry, is just going to be the change in. So for example, if we see delta H, that's the change in enthalpy, or the change of heat in the system. Or we can see delta S, which we'll talk about another time, is the change in entropy. So therefore, delta T is going to be the change in temperature. Now, of course, we can use degrees Celsius for this. This is typically what we see, but also we can use degrees Kelvin. Now, if you're wondering why these are interchangeable, 1 degree Kelvin, change in 1 degree Kelvin, is equal to 1 degree Celsius change. So therefore, we can use these interchangeably. However, we'll see that typically throughout chemistry, we'll be using degrees Kelvin, especially when we go over gas laws. All right, so let's get started on how to solve some of these problems. So let's take a look at this. A student must use 225 milliliters of hot water in a procedure. Calculate the amount of heat required to raise the temperature of 225 milliliters of water from 20 degrees Celsius to 100 degrees Celsius. The first thing to approaching a heat problem is writing your equation. If you're in New York State taking a chemistry regions course, this will be found in the reference tables on table T. Otherwise, this will usually be given to you somewhere on the exam. Okay, now we know that we're using this equation Q equals mc delta T because there's a change in temperature. If there wasn't a change in temperature, we would look at a couple different equations. But for now, let's focus on using Q equals mc delta T. So the easiest way to approach these type of problems is plugging in what you know and then solving for what you don't know. Now, right off the bat, I can tell you we're calculating the amount of heat because that's what the question asks you. But let's start plugging things in. So Q equals, well, what is M? Did we get the M from this? Yes, 225 grams. Now, what is the C? Now, the C can be found in one of the tables in the reference tables, table B, 4.18. I like to add the 4 just because I'm a little extra that way. Now, what's the change in temperature? Now, don't forget, delta T equals the final temperature minus the initial temperature. Now, this is very, very important that we remember this, because if we don't do the final temperature minus the initial temperature, we won't be able to determine if Q is negative or positive to determine if the problem is asking about an exothermic reaction or an endothermic reaction. Now, in this case, we're going to do 100 minus 20. Now, don't forget about units. Units are very important, but I'm not including them here so that we don't crowd up the screen too much. Okay, so now we have all variables in there, and we know 100 minus 20. I'm hoping we know this. 80. So now I'm just going to multiply across. I did the math for you, and we're going to get 755,312 joules. That's a very large number. So what we can do is we can just round this up to 75.5 kilojoules. Very simple. So we just solved for Q. We're going to double check from our question if that's what we were looking for, and we see calculate the amount of heat. So therefore, we calculated Q. So we know we answered the proper problem. All right, so let's take a look at another couple of variables. So calculate the specific heat. I'm going to move this of a new alloy if a 15.4 gram sample absorbs 393 joules, was heated from 0 degrees Celsius to 37.6 degrees Celsius. So here we don't know the C. Q equals MC delta T. Right over here, it tells you that we're calculating specific heat capacity. But if we weren't paying attention, we should just plug in what we already know. So we know 393 joules for our Q. We know our mass is 15.4 grams. We're solving for C. And we know the change in temperature right over here. So the change in temperature, the final is 37.6 minus 0.0 degrees Celsius. So that makes things a lot simpler. So let's just simplify this a little bit so we can solve algebraically. So 393 equals 579.04 times C. Now be careful because specific heat capacity is indicated by a lowercase c. It's kind of hard to see when you're writing things out. A capital C is going to indicate degrees Celsius, so try not to get those messed up. Now, if I simplify this further, I'm going to get C equals 0.679, and our units are joules per grams per degree Celsius. So again, all we did was we plugged in what we were given from our problem, and then we're solving for our unknown variable, which is specific heat capacity. Now, of course, we should check, and our answer is C, and the question is asking for C. That's a pretty simple problem. Now let's try solving for a different variable. This time, the question asks, a 40.0 gram sample of ethanol releases 2,952 joules as it cools from 50 degrees Celsius. Calculate the final temperature of the ethanol. So here, we're not given the change in temperature, so we're going to be solving for delta T. Okay, so let's write this out. Again, we should write out our equation. Q equals MC delta T. Of course, we're given our Q, 2,952 joules. Of course, we're given our mass, which is 40.0 grams. Now, C is not given here. Usually you would find this on a reference table. In the case of New York State, you won't find the specific heat of ethanol on those reference tables. But if the question were asking you something about ethanol, they would be providing it to you. So I will just give this to you. And C is actually equal to 2.46 joules per grams degrees Celsius. 2.46. So let's plug this in over here, 2.46. And now we're going to be solving for delta T. Okay, now let's plug this in, get this going. Now don't forget releasing energy. I'm going to have a negative Q. So make sure if you're releasing energy, the Q is negative. If you're absorbing energy, the Q is positive. So you do have to pay attention to the negative signs and the positive signs. 29, 52. Now multiplying across, I'm going to get 98.4 delta T. Doing a quick little bit of algebra here, we're going to get delta T is equal to, and our delta T is actually equal to negative 30 degrees Celsius. And we know that's the case because our delta T is going to be negative if we're releasing energy. So our final temperature is going to be lower than our initial temperature. Okay, now we know that delta T is equal to T final minus T initial. Now this is super important because we just solved for delta T, but the question is actually asking for the final temperature of the ethanol. So now we can plug that in, negative 30 degrees Celsius. So we plugged in our delta T that we solved for. And we don't know our final temperature because that's what the question is asking for. But we do know our initial temperature, and our initial temperature is 50 degrees Celsius. Okay, and again, solving algebraically, which I'm not going to show every single step of here because we should know algebra by now, equals 20 degrees Celsius. So now we solve for the final temperature. And because we have to pay attention to negative and positive signs, we should just double check things. So if there's energy released, then the final temperature is going to be lower than the initial temperature. So the final we calculated is 20 degrees Celsius, and our initial told to us was 50 degrees Celsius. Our final temperature is lower than our initial temperature, so we put the right sign. That's the way we can double check ourselves. It's always important to double check yourself because especially when you're using some algebraic equations like Q equals MC delta T, we want to make sure that we're putting in the proper variables, the proper positive and negative signs, and we should be checking units throughout. Okay, and that's pretty much it for everything. Of course, if you have any questions, please feel free to drop a comment. If you like this video, drop a like. And next video, we're going to be talking about heat capacity compared to heat of fusion and heat of vaporization.